Okay, so today we're going to be talking about complete and net ionic reactions. If you remember from when we talked about this last time, if we have a ionic compound which is soluble in water, in other words, this is going to be aqueous, it is going to dissociate. All right. So when it dissociates like this, it breaks apart into the anions, or the anions and the cations, like so. So we're going to be using this fact and what we talked about, how these things actually break up. So if you want, definitely need to look at the solubility video, before going through this here. So anyway, we'll be looking at a reaction that we had earlier, which was down here. The lead nitrate and some potassium iodide makes the lead iodide and the potassium nitrate. So we're going to be looking at that and seeing how we can form the complete and net ionic reactions from this one here. All right, so first of all, I'll just write out that equation again. All right, so that's the exact same equation we started with. Now what we're going to do is use this little flowchart. And this is, of course, the thing which is on D2L. So, definitely refer to this while we're going through this here. All right, basically what we're going to do is look at each part of the reaction here. And then using this flowchart, we can determine, how we're supposed to deal with this. So the first thing is we just start up here, and this asks, is it soluble? And of course, this is also referring back to our solubility rules that we have over there. But, is this soluble? So yes, if you remember from the solubility rules, and you can always just refer back to them, anything that has a nitrate is going to be soluble. So yes, that's soluble. Does it have the little aqueous there? Yes, it has the aqueous. And is this an electrolyte? So yes, lead nitrate is an electrolyte. Now, of course, there are some things like sugar and acetone and ethanol down here. I think I can... Yeah, which are soluble, like some of these things like methanol, ethanol, sugars, acetone. These things can be soluble in water, but of course they are not electrolytes, so they would not break apart because they don't have anions and cations in them. Okay, so is this an electrolyte? Yes. Okay, so everything here is satisfied. Is this a weak electrolyte? No. For example, weak acid. And really, for these weak electrolytes, the only ones we're going to be dealing with are weak acids, and we'll come back to this one a little bit. But for right now, there's actually no acids in this entire formula here, so that's not a weak acid. So what we're going to do is break this apart, write it as an anion and a cation, and then include the charge and also the aqueous, and we just keep doing this, and we'll have the complete ionic reaction. So we'll start up here for the lead nitrate. All right, so that's the first part, and really, for each molecule in here, we need to go through this first part of the flowchart here. Of course, I didn't make it too ridiculously complicated with too many arrows, but this is the basics, what we need. So we did the first one for the lead nitrate. Now we do the same thing here for the potassium iodide. So yes, this is soluble. All potassium compounds are soluble. Has a little aqueous, and this is definitely an electrolyte because it's a cation and an anion in there. Not a weak electrolyte. This is not a weak acid. So therefore, we're going to again break it apart, right, as the anion and the cation. So that's that part. Now for the lead iodide. Is this soluble? No, it's a solid. Does it have the little aqueous? No. Is it an electrolyte? Well, it could be, if it was actually breaking apart, but again, here, this is a solid compound, so really, that's a no. So at this point, we just leave it alone. You just write it exactly the same as what you found it. Okay, then we move on to our potassium nitrate. Again, my potassium nitrate, anything with potassium or nitrate, is going to be soluble. So yes, this is soluble, has a little aqueous, it is an electrolyte because they have the metal and a non-metal anion in there. So yes, we break that apart again. All right, now what you will notice first of all is that when we are dealing with complete ionic reactions, they get very long very fast. This, is done correctly, but now how do we actually check to make sure that everything is correct? So here, are the charges on both sides balanced? Okay, meaning that, the charge here on the left-hand side has to be equal to the charge on the right-hand side. So we just go through here and start adding up all my charges. So that's going to be plus 2. This one is going to be 2 times a negative 1. This one is going to be 2 times a positive 1. And then this is going to be 2 times a negative 1. And of course, that's just 2 minus 2 plus 2 minus 2. So this whole thing here is just 0, right? So that's just 0. All right, and now when you're dealing with these net ionic reactions, or when you're dealing with complete ionic reactions, usually these things should be 0 that we're dealing with. Net ionic reactions, there's definitely a possibility we could have non-zero things here. So all that really matters when we're dealing with this is that it's the same on both sides. And then over here, well, this thing, now you might say, well, do I have to figure out the charge on the ions? No, you're just looking at how it's actually written here. So there is 0 charge on the lead iodide because it's a solid, so there is no charge on this. So that's just going to be 0. And then again, that's going to be 2 times my plus 1 plus 2 times my minus 1. Of course, that's still going to be 0 once you add everything up. So that's going to be equal to 0. So yes, all my charges are balanced. So that's good. Do I have the same number of atoms of each element on both sides? I have 1 lead on both sides. I have 2 nitrogens on both sides. That's going to be 6 oxygens, right? I have 2 potassiums, and I have 2 iodines. Okay, so that's good. Do you have the same number of atoms of each element as you did in the balanced molecular equation? That's a big one. So right here, I have 1 lead up there. I have 2 nitrogens. I have 6 oxygens here. I have 2 potassiums. I have 2 iodines. Same thing here, 1 lead, 2 iodines, 2 potassiums, and 2 nitrogens, and 6 oxygens. Or you don't have to really count all the nitrogens and oxygens. If you just see right here, oh, I have the same number of nitrates as I do up there, you're still good. And do you have the aqueous, solid, liquid, or gas there? Well, here I got all my little aqueuses. This is my solid. Everything else is aqueous. Since we have all of that here, and if we didn't, then you go back and try again. Because this, especially like right here, this is where people usually goof up. We have here like the 2 potassium iodides. They write this as 2 potassiums but only 1 iodine. Or you forget here that the NO3 needs to be broken apart like this. Again, we talked about similar things when we were talking about here like the lead nitrate. So remember when we talked about the solubility stuff. Also, just remembering that there are in fact 2 of these, here, and of course, sometimes they accidentally break up the solid one. So, there's a bunch of ways you can goof this up, but if you follow through the flowchart step by step, you should reduce the probability of some errors there. So this is the complete ionic reaction right now. So this is complete ionic. But now what we can do is simplify this down dramatically by making just the net ionic reaction. So if you think about what's actually going on in here, we have a container here with lead ions and nitrate ions, and this has been mixed with a container of potassium ions and iodine ions. And all these things mix together. Eventually, the lead ions bump into the iodide anions. They fall in love, make little lead iodide babies, and everything else is still going to be in solution. So what's going on here is that the potassium and my nitrate ions, nothing has happened to them. They're still just floating around in solution, completely oblivious to what's been going on around them here. Okay, so this is where we start going on into the spectator ions. Okay, so if we have here the same ion on both sides of the arrow and the same charge, and both of them are aqueous. Now this is the important thing. We'll see an example of this later. They have to both have the same charge, and both of them have to be aqueous. So right here, the lead is aqueous over here. It's in the solid form over here, and it's not the same form as it is over here. So there's a big difference, so that's different. My 2 nitrates, these are exactly the same, right? So this one is exactly the same right here as this one, because it's NO3 minus aqueous, NO3 minus aqueous. My potassiums, K plus aqueous, K plus aqueous. And I have 2 of them, so both are exactly the same. My iodides, this is I minus aqueous. Now it's bound to lead, and it's in the solid form. So these are different, okay? So all the ones here that I've underlined are going to be my spectator ions, right? So if they're the same charge and everything in that, these are the spectator ions, and then you just remove them. Because the spectator ions, they're spectators, they're just observing, they're not participating in the reaction. I could very easily go here and make this lead acetate or sodium iodide. The same reaction would still happen. I would still be making my lead iodide here. But, instead of potassium, it could be sodium, or instead of nitrate, it could be acetate. So these still ions could just be floating around, but they're not actually participating. This is why they're spectators. Okay, so all the red ones here, these are my spectator ions. So now if we just remove these spectator ions, what we're left with is... So what we're left with here is the net ionic reaction. And remember, these were the ones that were left over from the spectator. So that's my lead and my iodide. So now, again, to check that we've done this correctly, are the charges on both sides balanced? That's going to be here, plus 2, well, times 1, plus 2 times a minus 1. That's, of course, going to equal 0. And this whole thing, if there's no charge on that, that's just equal to 0 as well. So 0, 0, that's happy. Do I have the same number of atoms of each element on both sides? I have 1 lead, 2 iodides, yes. Do I have all my little aqueous and solid labels on there? Aqueous, aqueous, and solid. Okay, so at this point, this is what we refer to as the net ionic reaction. That is your net ionic reaction. So if you didn't, well then you just have to go back, double check that you put all your atoms there. Again, the things that people usually do is they forgot the 2 in front of the iodine, or you forget your charges, or forget your aqueous signs. Very typical, and if we got everything right, we're very happy, we can, do this. And also down here, I've also listed, how we actually do break these things apart. So for instance, if I have here 2 iron sulfates, and this would be actually iron 3 sulfate, this would break apart into 4 iron 3 ions plus 6 sulfate ions, right? Because that's going to be iron 2, or sorry, 2 irons here plus times the other 2 there, so that's going to be 4 total. And then again, 2 times 3, that's going to be 6. That's going to give me 6 sulfates aqueous. But again, do not break this apart as, these weird, like a tri-ion here, or breaking apart into the individual sulfurs, or breaking this apart into like an iron 2 and putting the +3 with that weird stuff. No, all this stuff is just wrong. This is the way, you're supposed to do it, like this. Don't try doing anything else because it's not right. So this is the right way. Every other way is wrong. So what we mentioned before was over here talking about, is it a weak electrolyte, a weak acid? Now, of course, on the handout here, I list here the strong acids. And if you know the strong acids, and let's say you're dealing with another acid that's not a strong acid, well, then it is going to be a weak acid. So as long as you know what the strong acids are, everything else that's an acid is by definition going to be a weak acid. So what does this mean? Now, all the weak electrolytes that at least we're going to be dealing with in this class are going to be weak acids. So you don't have to worry about something which is soluble and maybe a base, or soluble and a salt that's a weak electrolyte. Or just worry, if it's a weak electrolyte, if it's a weak acid, that's your weak electrolyte that you're actually worrying about. All right, so for example, let's see, I have here phosphoric acid. Now, when this breaks apart, it will form. So phosphoric acid here, again, is a weak electrolyte, so we have these double arrows here indicating that it does set up an equilibrium and it's not 100%. So this phosphoric acid can break down into the dihydrogen phosphate anion plus a hydrogen ion, and then this, of course, can further break down to 2 hydrogen ions and a hydrogen phosphate anion, or it could go all the way to 3 hydrogen ions and then the regular phosphate anion. Now, when it's doing this, the thing is, for these weak electrolytes, more than 99% is going to be in this form. All the rest of these anions right here is going to be less than 1%. All right, and that's why, when we're dealing with these weak electrolytes, it says over here that if it is a weak electrolyte, we just leave it alone and write it as a neutral molecule, because 99% of the time, that's going to be true. All right, so this is why for the weak electrolytes, or I should say weak acids that we're going to be dealing with, we just write them as the molecule, because 99% of the time, that's the form that they are actually in. Conversely, if we're dealing with a strong acid, so a strong electrolyte, like a strong acid, a strong base, a soluble salt that we've been dealing with, when we have here, for instance, HCl, approximately 100% is actually in this form. There might be, a couple of molecules, of HCl there, but approximately 100% is going to be broken up like this. And this is, again, why, if we're dealing with these, it's a strong acid, then we're going to break this apart and write it as the cations and the anions, because, again, in water, this is the form that you will actually find these. All right, and then as another example here, let's look at what happens when we mix hydrochloric acid and sodium hydroxide. So here, this is hydrochloric acid, sodium hydroxide makes water and salt. So if you mix these in the proper proportions, you make lovely salt water. All right, now we will go back here, go through our little flow chart again and break this apart. So hydrochloric acid, is this soluble? Yes. It has a little aqueous there. It is an electrolyte, so that's good. This is a strong acid. HCl is a strong acid, so we just will break it apart and as cations and anions. And we do the same thing here for the sodium hydroxide. Sodium hydroxide is soluble. Anything with sodium is always going to be soluble. It has the aqueous. It is an electrolyte. This is not a weak acid. And again, you're just going to break it apart just like we did. Okay, now for water. Is water soluble in water? Well, yeah. Does it have the little aqueous? No. So therefore I leave it alone. I write exactly as just as water. And then as for my sodium chloride, this is soluble, definitely. Has a little aqueous, yes, and it is an electrolyte. It's not a weak electrolyte, so therefore I'm going to go here and break it apart. So this is going to be my complete reaction, complete ionic reaction. So again, down here we'll just go and say, okay, are all my charges balanced? +1, -1, +1, -1. Everything here is 0. That is 0. That's +1. That's -1. So everything on this side is 0. Do I have the same number of atoms on each element on both sides? I have here 2 hydrogens, an oxygen, 1 chlorine, 1 sodium, 1 chlorine, yes. Does this have the same stuff as my balanced molecular equation above? Well, yes, that's 1H, 1Cl, 1Na, 1OH, 1 water, 1Na, 1Cl. Yeah, and I have all my little labels on there, so that's good. And then we can go here. So that's my complete ionic reaction. We're done. And then at this point is the same ion on both sides of the arrow. And they're both the same charge in both aqueous. These are my spectator ions. So here, my H plus, that is now obviously different. My Cl minus aqueous, Cl minus aqueous, so that's going to be there. My sodium plus aqueous, that's the same. That's the same. OH aqueous, it's not over here, right? So that means that my chlorine and my sodium are my spectators, right? Because they're the same form on both sides. So we're just going to write what's left over here. So H plus plus OH minus gives me water. All right, and again, are the charges on both sides balanced? Plus 1 minus 1, 0. That is 0. Same number of types of elements on both sides. Do I have all my labels? Plus, one. I have 2 H's, 1 O. Yes, everything there is nice and happy. And then we're all good there. Now, if we have something like this is really going to happen for any strong acid and strong base. Okay, if I have any strong acid and strong base, the other stuff is just going to be spectators. So this is just going to be H plus plus OH minus gives me water. And really, if you do this kind of a reaction, and let's say I'm using HCl and sodium hydroxide to give me water, this will actually release a lot of heat. It'll get quite hot. It's a very exothermic reaction. Well, let's just say you flip it out and say you're going to use nitric acid and potassium hydroxide. You basically get the same temperature increase. It might be a little bit different because of the differences in specific heats and everything, but the amount of energy that's released is basically just dependent upon this reaction. It's not really dependent upon the spectators that are in your solution because they are not actively participating in the reaction there. All right, now let's just try pretty much the same reaction, but let's just change one of the atoms in here. So this is pretty much the exact same reaction, except instead of hydrochloric acid, I now have hydrofluoric acid. All right, now how is this going to look? So here, we'll start off again with my hydrofluoric acid. So is this soluble? Yes, that's soluble. It has my little aqueous. Yes. It is an electrolyte. Yes. Is this a weak electrolyte? Yes, it is. Hydrofluoric acid, remember, is not a strong acid. That is one of my weak acids over here. So right here, under my weak acids is hydrofluoric acid. So this is a weak acid. So since this is a weak acid, this is going to be left alone. We're just going to write it as we found it. All right, and then we'll do the sodium hydroxide. And again, this is exactly the same as what we had. It's the same molecule, so I'll just write that again. My water is exactly the same like we saw. And then my sodium fluoride. Again, remember, all things sodium are soluble. So right here, it is soluble, has a little aqueous after it. This is not a weak electrolyte, so therefore I'll break my sodium fluoride apart just like I did with the NaCl. So this right here is going to be my complete ionic reaction. So, like we did before, and I'll just let you verify that all my atoms and everything are the same on both sides here. Now we want to go here and identify my spectator ions. So here, HF, there is no HF on the other side here, so that's not a spectator. My sodium, this is going to be a spectator now because it's the same on both sides. And my OH, that just goes away. So really, in this case, only my sodium in this case is a spectator. And that's fine. There's not always going to be nice balanced charges for everything. So now we can just go here, eliminate my spectator ions, and then we will just be left here with the net ionic reaction. And this is going to be my net. If we look here at the charges, that is 0, that's minus 1, that's 0, that's minus 1. So as you can see here, the charges are not actually 0, right? That's 0, minus 1, 0, minus 1. So they're both the same charge on both sides, even though they're both not 0. But that's fine. We don't care if they're, all we care about is that they are the same charge, not that they are both 0. Okay, so that's the thing. Here I have two hydrogens, a fluorine, and one oxygen on both sides. That's happy. So otherwise, this is fine. This is my net ionic reaction for that. All right, and now let's see what happens if I put a weak acid and a weak base together. So here, this is going to be hydrofluoric acid. Copper 2 hydroxide gives me water, and copper fluoride. So again, we'll break this apart using our little flowchart here. And just like we saw before, hydrofluoric acid, this is a weak acid, so we leave this completely alone. And now for my copper hydroxide, this is not soluble. It does not have the little aqueous. This is an insoluble hydroxide. So again, we leave it alone. We just write it as a nice neutral molecule. My water, we saw before, that's a liquid. So again, we leave it alone. And then here, my copper 2 fluoride. If we go back to our solubility rules, all salts containing fluoride are soluble except for these. Copper is not listed, so we will assume that it is a soluble salt. So this means that this will be broken apart. All right, so then we just go through here, just verify that our charges are, everything is balanced. All we have the same elements and the same number of atoms on each side here. So here I have 2 hydrogens plus another 2 hydrogens, that's 4 hydrogens on this side. There are my 4 hydrogens over here. I have 2 fluorines, 1 copper, and 2 oxygens. So that's all good. This charge over here, that's 0. This is 0. So everything is there is obviously 0. This is 0. That's plus 2 minus 2 times negative 1. So this is going to work out to be 0. So everything is 0. So everything here is nice and balanced out. Okay, and this is my complete ionic reaction right here. Now, if we look here, what are my spectator ions? Well, there's no HF on this side, right? The copper hydroxide, it's not over here. So yeah, there are no spectators in this complete ionic reaction. That happens. So in this case, no spectators. That means that this reaction right here, this is complete and the net. So in this case, the complete ionic reaction and the net ionic reaction are exactly the same reaction here. That's, you know, some of the important ones just to kind of go through here. And then I also have a bunch listed here on the handout, you know, that comes with this. And we'll just go through explaining some of these, just so I don't have to write out everything over and over and over again. You can just, you know, refer to what's actually going on with this. All right, well, this first one we have up here, that's basically the same thing that we started with today, except in that case we have potassium bromide instead of potassium iodide. But it's exactly the same kind of a thing there, so we won't bother with this one. This one over here is kind of an interesting case. So we have here the sodium carbonate plus 2 hydrobromic acids give us sodium bromide plus water and carbon dioxide. All right, so again, all things sodium are soluble. So this breaks apart into 2 sodium ions plus the carbonate anion. Okay, again, there's my aqueous, and don't forget my little charges. Again, over here, hydrobromic acid. This is a strong acid. So this is going to break apart into 2 hydrogen ions plus 2 bromine anions. And then this is going to go over here. Now my sodium bromide, again, all my sodiums are soluble. So that breaks apart into 2 sodium ions plus 2 bromide anions. Again, both aqueous. And then my water, that's, you know, just left alone like we saw before. And here's my carbon dioxide, which is a gas in this case. And now, just referring back to this part, does it have the little aqueous? Well, no, carbon dioxide is a gas. So this is going to be CO2 gas. All right. Now, what are my spectators in this case? I have here 2 sodiums. Yep, that's the same. 2 bromines. Yep, that's exactly the same. So those are going to be my spectators. Also, we just want to verify that, you know, yes, all my charges are balanced, right? So that's going to be plus 2, minus 2, so that's 0. That's going to be plus 2, minus 2, that's going to be 0. There's plus 2, minus 2, that's 0. These are both 0. So yes, everything works out to be 0 in this case. And again, here I have 2 sodiums on both sides, 1 carbon on both sides, 3 oxygens over here. 1, 2, 3 oxygens. 2 hydrogens, 2 hydrogens, 2 bromines, 2 bromines. Okay. And again, you can just easily verify that the number of atoms is the exact same thing as we have up here and down here. All right, so once I eliminate my sodium and my bromine, which are my spectators, I'm going to be left here with my carbonate plus the 2 hydrogens, gives me water and carbon dioxide. And this is going to be my net ionic reaction. So just in case you haven't figured it out yet, this first row here, that's the balanced reaction. Then below there we have the complete ionic reaction, and then underneath there we have the net ionic reaction, and then obviously just the spectators. I just didn't put, only for this first one here, I put the labels because some of these equations got a little bit long and it was ruining the indentations and stuff. All right, and then for the next one here, we have 3 sodium carbonates and phosphoric acid. It gives us 2 sodium phosphates, water, and carbon dioxide. So again, just like we saw above, the sodium carbonates, these break apart, just like we saw. Phosphoric acid, remember, is a weak acid. So we leave this completely intact. And then, of course, we have here my sodiums. These break apart. So I'm going to have 6 sodiums, my 2 phosphates, and, of course, my 3 waters and 3 carbon dioxides, just like we saw. All right, now the big problem that a lot of people will have here is, especially when we're going from the 3 sodium carbonates, you're going to see here, you know, there's going to be 6 sodiums, right? That's 6 Na+. and then one carbonate, or 3 carbonates, right? That's 3 carbonates over here. And then down here again, we're going to have 6 sodiums and then 2 phosphates for that. So that's usually the area where people goof up, is forgetting to carry this 2. Remember, the 2 is multiplying everything in this equation through there. So there's going to be 2 phosphates for this entire thing. All right, now what is my spectator ions? Well, my 6 sodiums. These are the only thing that appears on both sides here. My carbonate and my phosphoric acid, they're only on one side, and everything else here is only on this side. So just taking out my sodiums, that's what we're going to leave here with 3 carbonates plus phosphoric acid gives us 2 phosphates, water, and carbon dioxide. And again, just verifying all our charges balance. 3 times -2, that's going to be a -6. 2 times -3, that's -6. And that's 0, this is 0, that's 0. So here both sides are -6, and then again, like I said, it's perfectly fine if your net ionic reaction has a net charge to it. Basically, these spectator ions are just around, just maintaining charge neutrality. You won't always have negative charges. You won't always have 0 net charge for your net ionic reaction. Let's see, for this one over here we have the ammonia and nitric acid giving us ammonium nitrate. So here the ammonia, that's just a gas, so there's nothing to break apart there, so we just leave it alone. Nitric acid is a strong acid, so that's H plus nitrates. And then here the ammonium nitrate, remember all ammonium things are soluble. So the ammonia breaks apart into NH4 plus aqueous, and then there's my nitrate aqueous. And again, what are things the same on both sides? Well, here we have NH3 gas. This is NH4 plus aqueous, very different. H plus here, no H plus on this side. Nitrate, NO3 minus aqueous, NO3 minus aqueous. Yes, these are both the same, so therefore my nitrate is going to be my spectator. And then after we eliminate my nitrate spectator, we're left here with ammonia plus hydrogen ion, gives us the ammonium cation. All right, and then the next one we have here, sodium hydroxide hydrochloric acid. We just did that one a few minutes ago. Then down here we have the copper hydroxide plus 2 HCl's. That's very similar to what we had before, although now we're dealing with a strong acid and the weak base. So here, the copper hydroxide again stays together. My strong acid, this stuff breaks apart, so that's 2H plus 2Cl minus. And then here, copper chloride. Copper 2 chloride is soluble. Remember from our solubility rules over here, all chlorides except for the copper 1. So right here, copper 2 chloride is soluble. So there's my copper 2 chloride, and then my water is just there. So the copper 2 cation and 2 chloride anions over here, plus 2 waters. And then here I have, then just have to look at what my spectator ions are. So copper hydroxide, that's obviously different. Here I have the copper in the solid form. Here I have it in the +2 form. My 2 hydrogen ions, they're not on this side. 2 chloride anions, yes, I have 2 chloride anions. So this means that right here, the 2 chlorides, these are going to be my spectator ions. So then we just write down here, copper hydroxide solid plus 2 hydrogen ions give me a copper 2 ion plus 2 waters. And right here you can see again, that's 0 plus 2, that's my plus 2, that's 0. And again, here I have 2 oxygens, 4 hydrogens, 4 hydrogens, 2 oxygens, and everything is nice and balanced there. So here we have copper hydroxide and 2 acetic acids giving us copper acetate and 2 waters. And really, this is the same procedure that we just saw here with the 2 hydrofluoric acids and the copper hydroxide, right? Because again, the acetic acid is a weak acid. So that means it's these, you can see right here, my complete and my net ionic reactions are exactly identical. Because in this case, my copper hydroxide doesn't break apart because it's a solid. My weak acid doesn't break apart because it's a weak acid. And then, of course, copper acetate is soluble. So that's just going to be my copper ion and my 2 acetate anions. And then, of course, my 2 waters. And there are no spectators in this case. All right, now this one might be a little tricky. And this is why, again, you always need to make sure you have your charges on your ions correct, because if you don't, it will look like no reaction is actually occurring here. Okay, so what we have there is, this is iron 2 nitrate, this is cerium 4 nitrate, and this is going to iron 3 nitrate to cerium 3 nitrate. All right, so that's what's changing here. Okay, so remember my nitrate is always -1 charge, so that means since I have 2 of them, this has to be iron 2. All right, so this is the iron 2 aqueous. My cerium, since this is a 4 nitrates, and nitrates are always -1, therefore my cerium here is going to be a +4. Now as for my nitrates, I've actually just combined them here because it doesn't matter where your nitrate actually comes from. So this is going to be 2 nitrates from here plus 4 nitrates from here. So that's just 2 plus 4. That just gives me 6 nitrates. And then over here on this side, now notice I have now 3 nitrates with my iron. So that's going to mean that this is now an iron 3 anion, or sorry, iron 3 cation. And then over here, I have now 3 nitrates with my cerium, meaning that the cerium is also going to be a plus 3. So now this is going to be cerium plus 3 over here. And again, that's going to be 3 plus 3, that's 6. I'm going to have 6 nitrates over here. Now what are my spectator ions? My 6 nitrates, both of these just go away. So my nitrates, these are my spectators, they go away. I erase those, and I'm left here iron 2 plus cerium 4 gives me iron 3 plus cerium 3. Okay, and this would be your net ionic reaction. And again, going back to what we saw here, the spectator ions, the same ion on both sides of the arrow, in other words, both same charge and both aqueous. Well here, iron 2, iron 3, cerium 4, cerium 3. They are both aqueous, but they are not the same charge. So for this reason, that's why these are not erased. And again, just to make sure that the charges are balanced, plus 2 plus 4, that's 6. 3 plus 3 is 6. Okay, so everything here, number and types of atoms and everything, is nice and balanced. But it's a little bit unusual, and also why you always have to make sure you include the charges, because if you don't, it'll look like no reaction actually did occur. All right, down here, this is a pretty famous reaction. When you're having a copper sulfate solution, you put in some tiny zinc particles of the zinc metal, and you actually get copper metal to precipitate out, and you're going to be left with a zinc sulfate solution. So here I have my zinc, and this is solid zinc, so I'm leaving this exactly alone. Over here, copper sulfate. This is a soluble thing. So all sulfates are soluble except for these over here. Copper is not one of them, so copper is a very soluble salt. Zinc is again another very soluble salt. And then we're left here with copper metal in the solid form. So here I have my zinc solid plus my copper 2 plus aqueous plus my sulfate aqueous. Gives me my zinc 2 plus aqueous, my sulfate aqueous, and then the copper, you just leave that alone. So you can see right here, my sulfate is the same on both sides. My zinc goes here, again, watching your charges, that's zinc 0, because there is no charge on this, to zinc 2 plus, so that's obviously different. My copper 2 plus is going to copper solid, which is 0. So again, if we refer back to here, the same ion on both sides of the arrow, same charge in both aqueous. So here we're obviously violating that, since this one here has 0 charge and obviously is solid. Same here for the zinc. Okay, so since they're different, we now write them as part of the net ionic reaction down here. And sulfate, of course, is exactly the same, so that's my spectator. So I have solid zinc plus the copper 2 ion gives me the zinc 2 ion plus solid copper. Okay, and that's going to be my net ionic reaction. And again, you can very easily see 0 plus 2, 2 plus 2 plus 0. The charge is the same on both sides. Over here, I have magnesium hydroxide, solid, plus 2HF aqueous. The old version I had a little typo there, but the version that's on D2L, that's fixed. 2 hydrofluoric acids gives me magnesium fluoride, solid, plus water, liquid. Now, this is another kind of a little weird case here. The magnesium hydroxide, looking at our soluble hydroxides, most hydroxides are insoluble, except those of the alkali metals, calcium, strontium, and barium. Magnesium, over here, is not one of those included. Okay, so magnesium hydroxide is insoluble. Hydrofluoric acid, of course, is the weak acid we talked about, so that one's doesn't break apart. Magnesium fluoride, all salts containing fluoride are soluble except, there's my magnesium. So magnesium fluoride is insoluble. Okay, so that's my magnesium fluoride here. And then, of course, my water. So that means, since this is solid, I write it exactly the same way I found it. My hydrofluoric acid, that's a weak acid. I write it exactly the same way I found it, so nothing there breaks apart. My magnesium fluoride, that's a solid. I write it exactly the same way I found it. And water, of course, is a liquid. I write it exactly the same way I found it. So in this case, my balanced EM reaction, my complete ionic reaction, and since obviously there are no spectator ions, we don't even have any ions floating around in here, my net ionic reaction is exactly the same. So this is another, kind of a weird case, but it can happen where the balanced, complete, and net ionic reactions are all the same, because nothing here is actually doing any breaking apart into the ions in solution. And then down here, I have my barium hydroxide plus 2 hydrofluoric acids, and that's going to give me my barium fluoride solid plus water. Barium hydroxide, and we just saw that a minute ago, Remember, barium hydroxide is one of my soluble strong bases. So this will break apart into a barium ion plus 2 hydroxide anions, because I have 2 of them right there. So that's there. My hydrofluoric acid, of course, is a weak acid, so this is left alone. Barium fluoride, let's go to our solubility rules. All salts containing fluoride, there's my barium again. So the barium fluoride is going to be insoluble. So my barium fluoride is a solid, and water is, of course, water. So right here, this is going to be my barium plus my hydroxide ion, gives me HF, plus my barium fluoride solid plus water. This is my complete ionic reaction. And now as for my net ionic reaction, there are no spectator ions here, right? The barium is going from the aqueous into the solid form. My hydroxides have gone into water. My HF, well, the H has gone part into water, part into the barium fluoride. So there are no spectator ions. Everyone's participating. So since there are no spectator ions, the complete and the net ionic reactions in this case are exactly the same. All right, and then down here on the bottom, we have a very complicated equation, but again, just using all the rules that we have, this is tedious, but very possible to do. So here I have potassium permanganate. Now, of course, we haven't dealt anything with the permanganate anion in any of our solubility tables, but if you remember, everything that contains potassium is going to be soluble. So that means that my potassium permanganate is going to break apart. Hydrochloric acid, this is a strong acid again, so this will break apart. My iron chloride. All the chlorides are soluble except for a couple of examples there. So again, my iron chloride here will actually break apart. So here I have one potassium. My permanganate MnO4, that's the complete anion right there. It's one of those oxy anions. It actually has a lovely purple color. So this is my permanganate, KMnO4. So again, that's going to be minus aqueous. And again, even if you didn't know what the charge on this was, the potassium's +1. So my permanganate has to be a -1 charge. Then here my hydrochloric acid, that's going to be 8 H pluses. And then for my chlorines, there's 8 over here, plus that's 5 times 2, that's 10. So that's going to be 8 plus 10, which is 18. So that's why I have here 18 chlorides aqueous. And then for my iron, that's going to be 5 iron. And now this is 2 chlorines, so that means this has to be an iron 2. So that's going to be 5 times my 5 iron 2 aqueous. Okay, so that's everything over here on this side. And then when I continue on here, my potassium chloride, that's going to be something which is soluble. So I break this apart into my potassium ions. My chloride, again, is going to be included here with my manganese and my chlorine from my iron chloride. So there's going to be here 1 plus 2, so that's 3, plus another 5 times 3, or 15. So 15 plus 3, that's 18 chlorides in this case. My manganese in this case, and this is a redox reaction, by the way. So the Mn is going to become the +2 charge in this case. So that's MnCl2 aqueous. Now, as for this, you may be wondering, well, wait a minute, I thought these things aren't supposed to break apart. This is a redox reaction. Those things can actually happen in those cases. Don't worry about the rules. If we do cover that later, we'll get into all the rules about redox reactions. But if I do give you anything like this, the balanced reaction will be explicitly shown. As to actually figuring this out from redox rules, that's a whole other thing we're not going to worry about right now. All right, so we have there my manganese 2+ aqueous. Now this is going to be iron 3. So that's going to be, because here I have 3 chlorides, so that has to be iron 3 aqueous, plus my 4 waters, which are liquid. Now what are my spectators here? Notice my potassium. There's my potassium. My manganate, my permanganate, and gone to manganese 2. That's obviously different. My 8 H pluses. That has gone to waters, so that's obviously different. My 18 chlorides, that's exactly the same. And here my iron 2 has gone to iron 3. So those are different. So that means my spectators here are just going to be my potassium and my chloride. So once we eliminate those, we have there the permanganate, the 8 hydrogens, the 5 iron 2s, gives me a manganese 2, and 5 iron 3s, and 4 waters. And again, you can very easily just go through there and verify that all your charges balance. So here, that has 1 manganese on both sides. I have 4 oxygens, 8 hydrogens, 8 hydrogens, 5 irons and 5 irons. And then as for my charges, that's -1, that's +8. This is 5 times 2, which is 10. So that's going to be 10 plus 8, that's 18, -1, that's 17. And then over here, water is 0. 5 times 3, that's 15, plus another 2, that's 17. So yes, this is +17, that's +17. My charges have balanced out. All these spectators are doing is just keeping my charge balanced and everything. So anyway, that's the basics of the net ionic reactions. Again, there are a bunch of examples here for you. Go through the flowchart. If you go through enough examples. So anyway, this is the flowchart. There are a bunch of examples here. Go through them, follow through with the flowchart. If you do it enough times, it becomes almost second nature. Look at the examples here, understand why I'm doing every little thing I'm doing. That's why I made up the little examples here for you to practice with, and hopefully this will help you out understanding how to do net ionic reactions. All right, and this is probably a ridiculously long video again, so I will stop it there before you fall asleep.